Bismillahirrahmanirrahim. Assalamu alaikum. Lecture number 7, unit number 1, complex number. The topic of this video lecture is real and imaginary parts of such type of a complex expression. If we given x plus iota y power n, so how we can find out its real and imaginary part? N may be +1 or -1, +1 or -2. We know that x plus iota y is a complex number. So you see that if there is a power, n mean 1, so if is n equal to 1, so it is so simple that x, this is equal to x plus iota y. So according to the definition, x is a real part and y is imaginary part. Y is imaginary part. But if the value of n is equal to -1, or if the value of n is equal to +2 or -2, then how we can find out the real and imaginary parts of this type of a complex number? Then we also need to know that how we can find out the complex number, the real and imaginary parts of such type of questions. X1 plus iota y1 mean this is a complex number. This x2 plus iota y2 is also a complex number. These two complex number are in division, quotient form, and there is also whole power n. This n may be +1, -1, or +2 or -2. So how we can find out the real and imaginary parts of such type of questions? Then we will discuss the exercise question from exercise 1.2. Now to begin with the real and imaginary part of such type of numbers, we need to briefly revise the previous knowledge that we studied in the previous lecture. In the previous lecture we discussed the properties of complex number. Now you know that the properties of complex numbers are closure property with respect to addition and multiplication, and closure property is hold in the set of a complex number. We discussed in detail in the previous video lecture. Closure property mean if you add two complex number, you will get again a complex number. If you multiply two complex number, you will get again a complex number. So the set of complex numbers are closed with respect to addition as well as with respect to multiplication, which is called closure property. So closure property with respect to addition and with respect to multiplication are hold in C. C mean set of complex number. After that we discussed the commutative property. So commutative property with respect to addition as well as with respect to multiplication are hold in the set of complex number. That is z1 plus z2 is equal to z2 plus z1. This is the, if you add z1 with z2 or z2 with z1, you will get the same answer. This is true for all complex number. And and with respect to multiplication, the commutative property is also true. Z1 multiplied by z2 is equal to z2 multiplied by z1. So this is the commutative property. Then we discuss the associative property, which is also true in the set of a complex number, and then the distributive property of multiplication or addition, which is actually the correct name of that property is left distributive property of multiplication or addition. And I also mentioned that when a number is multiplied from the right side, for example this is z1 plus z2 and multiplied by z3, which is equal to z1 z3 plus z2 z3. So this is also a commutative property, but you see that z3 is multiplied from the right side with z1 plus z2. So this is the distributive property of multiplication or addition, but the correct name, the precise name of this property is the right distributive property of multiplication or addition, and that which is given in your book, first year book. So that is z1 multiplied by z2 plus z3, which is equal to z1 z2 plus z2 z. So this is the left distributive property of multiplication over addition, because you see that in this case the z is distributed over z2 and z3 from the left side, and in this case z3 is distributed over z1 and z2 from the right side. So these are the distributive properties. After that, we discussed in the last video lecture what is the additive identity. We defined and we briefly we in detail discussed that why 0 plus 0 iota, which is a zero complex number, is the additive identity. So remember, this is a zero complex number, this is the additive identity in the set of complex number. Additive inverses are very this is unique for all set of complex number. Additive identity is a single, but additive inverses are every number has its own additive inverse. Every complex number has its own additive inverse. If you add two complex number and you get the additive identity, then those two complex numbers are said to be additive inverses. So remember that for every number there is different additive inverse, but additive identity is unique. Similarly, we discussed that 1 plus 0 iota is the multiplicative identity. According to definition, we discussed this in detail, that whenever you multiply 1 plus 0 iota with any complex number, you will get that complex number. So that's why 1 plus 0 iota is called the multiplicative identity. And multiplicative inverse is, if a plus b iota is your complex number, then the multiplicative inverse is a divided by a square plus b square plus minus b divided by a square plus b square iota. So this is your multiplicative inverse. If a is, let's say, 3 plus 4 iota, so you just need to replace a by 3 and b by 4. So that will become, in this expression, so that will become the inverse of that, multiplicative inverse of that given complex number. Whenever you multiply the inverses, you must get an identity. So if a plus b iota has multiplicative inverse a divided by a square plus b square plus minus b divided by a square plus b square iota, so it means that when you multiply this complex number with this, you must get the multiplicative identity 1 plus 0 iota. So this is all from the previous video lecture. Now coming towards the today's topic, which is the real and imaginary parts of. So you see that this is the in this lecture, first of all we will search for that how we can find the real and imaginary parts of such type of numbers, and how we can find the real and imaginary parts if we have given such type of expression. In numerator there is a complex number, in denominator there is a complex number, and there is a whole power. This n is equal to plus 1 or minus 1, or n equal to plus 2 or minus 2. So the values of the n are maybe 1, maybe minus 1, maybe plus 2, maybe minus 2. So this is the, if you see to the introduction of this lecture, as we discussed in lecture number 1, that the number of the form x plus iota y mean a plus b iota. Here we write in the definition that a plus b iota, instead of that you can write x plus iota y, where x and y are the real parts and iota is equal to under the root minus 1, is called the complex number. The complex number x plus iota y has x is a real part and y is imaginary part. So now the target of this video lecture is we focus that how we can find out the real and complex parts, real and imaginary parts of this type of questions, and how we can find out the real and imaginary parts of this type of questions. For that, now when n equal to 1, so this is so simple, you clearly see that part number 1, x plus iota y power n reduces to x plus iota y if n equal to 1. So in x plus iota y, x is the real part and y is the imaginary part. So this is so simple. Now if n equal to minus 1, here if I replace n equal to minus 1, so this x plus iota y power minus 1 is actually equal to 1 divided by x plus iota y. You must take the reciprocal. So this is x plus iota y power minus 1 is equal to 1 divided by x plus iota y. Now in this case You cannot say that x is my real part and y is my imaginary part. This is actually now the quotient of this is the quotient form. Now actually this is the quotient form. This is the quotient form, and in this quotient form the numerator is a complex number in which the imaginary part is 0. So this is a favor real number, although this is a complex number. 1 is a complex number, but its imaginary part is 0, so that's why this is a favor real number. And this is x plus iota y is a complex number. So this is actually the division of two complex numbers. So whenever we perform the division of two complex number, we do the process of rationalization. And what is rationalization? You will take the conjugate of the denominator and multiply and divide that conjugate with the given quotient form. So you know that x plus iota y has conjugate x is equal to minus iota, because in case of the conjugate we just change the sign of imaginary part. So here the imaginary part is plus y, so that will become minus y, so that is the conjugate. So now you see that in this quotient form is multiplied and divided by the conjugate of the denominator. The process is called rationalization. So now it is so easy. 1 multiplied with x minus iota y, and this x plus iota y will be multiplied with x minus iota y. So this will become x square plus y square. By using a square minus b square is equal to a plus b into a minus b. So you see that you get this. Now in this case this expression can be written as, you get this. Okay, now in this case you see that this can be written as x divided by x square plus y square plus minus y divided by x square plus y square iota. So therefore the real part is this and the imaginary part is this. So these are the real and imaginary parts when n is equal to minus 1. Now if n is equal to 2, so you see that this x plus iota y power n will be reduced to x plus iota y whole square, and then use the formula a plus b whole square is equal to a square plus b square plus 2ab. So you see that this is so easy. So x square minus y square will be the real part, and xy 2 multiplied by xy is the imaginary part. Whenever you take the consider n equal to minus 2, so that will become x plus iota y power minus 2. So that will 1 divided by x plus iota y power 2. Now take the conjugate of this denominator, because this is the division of a two complex number. So you will must do the process of rationalization to make the denominator real. Now in this case the denominator is not real, so this is the process of rationalization. The conjugate is just replace the sign by minus, because this is plus, this is the sign of imaginary part. So in conjugate the sign of the imaginary part is changed, so this is the conjugate. So you see that conjugate is multiplied and divided with the quotient form. Then you just need to simplify, so that will be the real part and that will be the imaginary part. So for these example you may try by using the same. In the part number 1 you see that this is already in the a plus b iota form or x plus iota y. So here 2 is the real part and minus 3 is the imaginary part. But in this case you will take the reciprocal of this. In this case you will use a plus b whole square formula, and in this case you will take the reciprocal and then the process of rationalization, and then you need to use the a plus b whole square formula. So this is the real and imaginary parts of x plus iota y whole power n. If now we have the question like x plus x1 plus iota y1 divided by x2 plus iota y2 whole power n. So what will be the real and imaginary parts if n equal to 1 plus 1 minus 1 plus 2 minus 2. So whenever I consider n equal to 1, so this expression will be reduced to this. So this is actually the division of two complex numbers, and whenever we perform the division you need to do the process of rationalization. So take the conjugate of the denominator, multiply and divide that conjugate with the quotient form, and just need to simplify. You will get the real and imaginary parts. The remainings are you can see this from the book also. So this is the idea that how we can find out the real and imaginary parts of such type of questions. Now switching towards the exercise 1.2. so this is the exercise 1.2. you see that this is the exercise 1.2. so we will solve these questions. This exercise is so much easy if you know the knowledge that we discussed in the previous two video lectures. So that will be this exercise will be actually the illustration of that work. So you see that I already written that illustration of the concept of lecture number 5 and lecture number 6. This is lecture number 7. Whatever we discussed in lecture number 5 and lecture number 6, that will be repeat here by just solving these questions. We all know that those properties. Question number 1, f z1 is equal to 2 plus iota and z2 is equal to 1 minus 2 iota 1 minus iota. Then verify the commutative property with respect to addition and multiplication. So you know the this is the commutative property with respect to addition, and this is the this is the commutative property with respect to multiplication. So first of all, you need to consider the left hand side, z1 plus z2. So this is z1 plus z2. Real part will be added with real, imaginary part will be added with imaginary part. So that will 3, this will be 0, so 3 plus 0 iota. Now consider the right hand side, z2 plus z1. So this is z2, this is z1. Add the real and imaginary, add the real parts and imaginary parts, you will get 3 plus 0 iota. So you clearly see that the right hand side, z1 plus z2 is equal to 3, and z2 plus z1, which is the right hand side, which is also equal to 3. So you see that z1 plus z2 is equal to z2 plus z1. So the commutative property is hold. Now commutative property with respect to multiplication, z1 multiplied by z2 or z2 multiplied by z1, the result must be the same. So you see that first of all I multiply z1 with z2, so I get 3 minus iota. Then I multiply z2 with z1, so I get 3 minus iota. So you see that both the left hand side and right hand side are equal, so hence commutative property with respect to multiplication is verified. Question number 2. In question number 2, z1 is minus 1 plus iota, z2 is equal to 3 minus iota, z3 is equal to 2 plus 3 iota. Verify the associativity or the associative property with respect to addition and multiplication. So you see this is z1 z1 plus z2 z3. So this is z1 z2 plus z3. This is the associative property with respect to addition. You see that z1 plus z2 plus z3 equal to z2 plus z1 plus z3. I already explained to you in this left hand side. You see that this bracket will perform first. So what does it mean? It means that when you add the last two complex numbers first and then the result of that is added with the first one, or if you add the first two complex number first and then that result is added with the last one, the left hand side and right hand side must be equal. So this is the associative property. So now z1 plus z2 plus z3. So this is z1. First of all, add z2 and z3 because they are in bracket, and then when you get a number, a single complex number, from this you add that complex number with the 1 minus 1 plus iota, and similarly this is the right hand side. So it is so much easy. Similarly with respect to multiplication, so this is the associative property with respect to multiplication. On the left hand side, you first perform z2 multiplied by z3, and then that result will be multiplied with z1. So you see that first I have multiplied z1 and z2 and z3, and then multiplied that result, which is 12 plus 5 iota, which comes from the multiplication of z2 and z3 with z1. So you get 17 minus 17 plus 7 iota. Now on the right hand side, first of all you will perform the multiplication between z1 and z2 because they are in bracket, and then the result of z1 and z2 will be multiplied with z3. So you see that I first of all I multiply z1 and z2, and then now you see that this is z3. So multiply the result of z1 and z2 with z3. So you will get minus 17 plus 7 iota. So you see that the right hand side and the left hand side are equal. So that this implies that the associativity property with respect to multiplication is hold in the set of complex numbers. Now similarly, this is the distributive property of multiplication over addition. So this is the distributive property of multiplication over addition. So you just need to take the left hand side. First of all you will add z2 and z3. First you will add, this is the addition, z2 and z3, and then the result which comes from this addition multiplied with z1, and on the right hand side you will multiply z1 and z2 and then z1 and z3 and then add those two results. So you will get the same answer. This is also very much easy. Now finding the inverse, find the additive inverse of the following complex number. So 5 plus 2 iota is a one complex number, and this is another complex number which is given in the ordered pair form. So if I want to find the additive inverse of 5 plus 2 iota, so I need such a number which is added to this 5 plus 2 iota, and I get additive identity. So when I add minus 5 minus 2 iota with this complex number, so I will get 0 plus 0 iota, 0 complex number, which is the additive identity. So whenever from the addition of two complex number you get additive identity, then those two complex numbers are the additive inverses of each other. And similarly, if I need to find the additive inverse of 7 comma minus 9, which is actually equal to 7 minus 9 iota, so I need to find such a number which is added to this, and I get 0 plus 0 iota, mean additive identity, which is minus 7 plus 9 iota. If added to 7 minus 9 iota, you will get the additive identity 0 plus 0 iota. So according to the definition, whenever two complex numbers are added and you get the additive identity, then those two complex numbers are said to be additive inverses. So you see that whenever I add minus 5 minus 2 iota with this, so you get 0 plus 0 iota. So this is additive identity. So that's why I am saying that these two are the additive inverses of each other. Similarly, when I add minus 7 comma 9 with this, so you will get 0 comma 0. So this can be written as 0 plus 0 iota. So this is the additive inverse. So the additive inverse of this is minus 7 comma 9, or you can write this is minus 7 plus 9 iota, and this can be written as 7 minus 9 iota. So these are the inverses, additive inverses of each other. Now in this case, z1 is equal to 2 plus 4 iota, z2 is equal to 1 minus 3 iota. You need to verify z1 bar plus z2 bar is equal to z1 plus z2 whole bar. What does bar mean? Bar represent the conjugate. So on the left hand side, first of all you will take the conjugate of z1, then conjugate of z2, and then those result will be added. But on the right hand side, first of all you will add z1 and z2 and then take the conjugate, because this is a whole conjugate. So you see that on the right hand side, conjugate of z1 plus conjugate of z2. So the conjugate of z1 will be this will be actually equal to this conjugate will be equal to this will be minus. Now you need to change the sign of the imaginary part. So this is minus 2 minus 4 iota. This is a mistake. 2 minus 4 iota is the conjugate of 2 plus 4 iota, and 1 plus 3 iota is the conjugate of this number. So now add these two conjugate. Now add these two conjugate. On the right hand side, first of all you will add and then take the conjugate. So the result on the both side must be equal. So this is the part number 1. Part number 2 is also similar. Now on the left hand side, first of all you multiply z1 and z2, then take the conjugate, and on the right hand side you take the conjugate of z1 and z2, then multiply that result. So you will get the same result. Now on this case, first of all you will perform the division, z1 divided by z2, and then take the conjugate. On the right hand side you will take the conjugate of z1 and the conjugate of z2 and then perform the division, and for the division you must do the process of rationalization. So this is also so much easy question. You see that from here. Now this is the remaining part of that question. So these are so much easy questions. Now in this case you see that show for all complex number z1 for all complex number z1 and z2. So this is z1 z2 whole absolute is equal to z1 absolute plus z2 absolute. Part number 2, z1 divided by z2 whole absolute is equal to z1 absolute divided by z2 absolute. Z2 is not equal to 0. I already explained that in denominator you must impose a condition that it must be not equal to 0, because whenever the denominator becomes 0, the division is not possible by 0. So what is the definition of absolute? If z is equal to a plus b iota, so then z absolute is equal to a square plus b square, which is the absolute value of a complex number, modulus of a complex number, or magnitude of a complex number that we discussed in the previous video lectures, that we are discussing the theory, so that we discuss. So now in this case, And if you need to verify this, if you need to show these two are equal, first of all you will consider the left hand side. For the left hand side, first of all you need to multiply z1 and z2. So first of all you will need to multiply z1 and z2, and then you will take the absolute. So now in this case you see that no specific value of z1 and no specific value of z2 is given, so that's why I am consider z1 is equal to a plus b iota and z2 is equal to c plus d iota. So first of all multiply these two and then take the, this is the multiplication of z1 is equal to a plus b iota and z2 is equal to c plus d iota. So this is the multiplication. Now take the conjugate, now take the absolute, sorry. So this is the real part, so this is the real part square, so this will be the real part square plus imaginary part square, this is the imaginary part square, so this is the imaginary part square and square root. So this is the definition of the absolute. Now in this case first of all you will take the absolute, so the absolute of this will be a square plus b square square root. In this case the absolute of this is c square plus d square square root, and then you need to multiply these two, then you need to multiply. So you see that the left hand side will become to the right hand side. And similarly this is the division, part number 2. First of all in on the left hand side you will take the division. So for division you must do the process of rationalization. You see that the process of rationalization. So when you take the division, so you will get this and then take the absolute. And on the right hand side, first of all you, now you see that this is the simplification, this is a simple simplification. You see it from here and then try yourself, then I am considering the right hand side, and you see that first of all I will take the absolute of numerator and the absolute of the denominator, and then use then that will be equal to this. You see that, so both the left hand side and right hand side are equal. So from here you can take half, and this is just a simplification, nothing more than that. Okay, now question number 7. Question number 7 is separate real and imaginary parts. So this is the first question. So now you see that this is not a single complex number, this is the division of two complex number. So first of all, to convert this quotient form into a single complex number, you need to perform the process of rationalization, because the denominator and the numerator consider two complex numbers, and in denominator there are two independent constants, 5 and -2. So that's why the process of rationalization, this is so simple, we explained this so many times. So the conjugate of the denominator is this, multiply and divide this conjugate of the denominator with this quotient form and simplify, you get this. So now in this case the real part is 4 divided by 29. This is the, also you can write RE of this. So this is the given quotient form for which we are finding the real and imaginary part. So the real part is 4 by 29 and the imaginary part is 19 by 29. Okay, so the remaining parts, these are the parts which are given in the example. So solve it by yourself, we already discussed this in theory. You just need to the process of rationalization, or a square minus b square is equal to a plus b, or a minus b, or you can use a plus b whole square is equal to a square plus b square plus 2ab. Now this is the part number 2 of this question, separate real and imaginary part. So first of all you need to convert the numerator by simplify the numerator by using a plus b whole square formula. So this is converted to this complex number in the given question, is converted to the quotient form. Now this quotient form can be solved by process of rationalization. So take the conjugate of the denominator and multiply and divide that conjugate with this quotient form and just simplify. So you will get the real part and the imaginary part. Similarly in that case you first multiply and divide the conjugate with the given quotient form and then simplify. So you will get the real and imaginary part. In this case real and imaginary parts both are equal, -1 by 2 -1 by 2. Similarly now in this case you see that 2a minus b iota power -2 separate into real and imaginary parts. So when you convert this into this form, so this is actually the division of two complex number, this is a quotient form. So you will do the process of rationalization, you will do the process of rationalization. So this is just a simplification. You get this is a real part and this is the imaginary part. So you can practice on that. You see that these are just multiplication and division and nothing more than that. This is just a simplification. This is just you need to do practice on that. Now in this case, this is 5 minus 2 iota divided by 2 plus 3 iota whole power minus 1. Separate into real and imaginary part. So take the reciprocal. So that will be converted into this. So this is actually the division of two complex number. Division of two complex number. So the denominator contain 5 minus 2 iota, its conjugate will be multiplied and divided. And then do the process. Just multiply the numerator with numerator and denominator with denominator. In the denominator you will use a square minus b square formula. So you get the real and imaginary parts. You get the real and the imaginary parts. Now this question is also similar. First of all, you can convert, this is a whole square, so the square will be of the numerator and then that square be also on the denominator. So the denominator consists of the complex number, so multiply and divide the conjugate of that denominator with this quotient form. This is the process of rationalization. So in this case also the process of rationalization is uses. Now question number 8 is also so simple. Show that z1 plus z bar is equal to 2re, mean the real part of z. So if z is equal to a plus b iota, in this case you didn't know about that what is it, so we generally consider that z is equal to a plus b iota. So the z bar of this will be, mean conjugate of z will be a minus b iota. So the left hand side is z plus z bar. So now this is your z and this is your z bar. So add this z with z bar. So this b iota will be cancelled with b iota because they are same and their signs are different, and this will be a plus a equal to 2a. So now in this case you see that the real part of z is a and z plus z bar is equal to 2a. So it means that this is actually 2 multiplied by re of z, because a is the real part. Re of z is a. So you see that from this left hand side you get 2a. 2a mean 2 times real part of z, because a is the real part. So this is the required proof. So these questions are also so easy. Similarly, if z is equal to a plus b iota, so this is equal to the z bar, then subtract z bar from z bar from z. So you will get 2b iota. But we know that b is the imaginary part. You know that b is the imaginary part. So just replace this b by im of z, because the imaginary part is denoted by im of z. So you will get the required right hand side. Similarly, multiply z1 and z2, so you will get this. Now you see that re of z mean a square, re of z whole square mean a square, and im z of whole square mean b square, because the real part of z is a and the real part, imaginary part of the z is b. So this is so simple. Now z is equal to z bar implies z is real. If the conjugate and the given complex numbers are equal, then it is possible only if z is real. Now you see that if z is equal to a plus b iota, so its conjugate is z bar is equal to a minus b iota. So if z is equal to z bar, so this implies that a plus b iota will be equal to a minus b iota. So this is possible only if b equal to 0. This equation is possible only if b equal to 0. So that is imaginary part of z is equal to 0. So if b equal to 0, then a equal to a. That is z is equal to a and z bar is equal to a. So implies that z is a real number because a belongs to R. So this is the part number 4 of the question number 8. Okay, now part number 5 is also easy. Part number 6 I explained. Question number 9 as I already explained in so much detail. So please study that question number 9 from this, and inshallah in the coming video we will discuss the question number 9 also, but just study this question number 9. Now you see this answer, study this answer from the page, practice on it, and I will explain this graph in next lecture. So question number 9 will be explained in the coming video lecture. Thank you.